So he is currently working as an assistant professor in the Department of Computer Science and Engineering uh, at Shiksha Anusandhan University, Bhubaneswar. He holds a PhD and MTech in Computer Science and Engineering from NIT Silchar in 2022 and 2016, respectively. His primary research interests lies in computational neuroscience, spiking neural networks, and the application of AI in healthcare. Over the years, Dr. Irsad has contributed significantly to these domains through his scholarly publications in reputed SCI, Web of Science, and Scopus Index Journal and conferences. Dr. Irsad is also actively involved in the academic review process and is a reviewer for high impact journals, including scientific reports under the Nature Publication Group and the IEEE Transaction on Cognitive and Development Systems. In recognition of his academic excellence, he was honored with the Anandoram Borua Award on December 17, 2006. This early accolade highlights his long-standing commitment to academic and research excellence. So, with this biography, the short biography, let us, along with Dr. Surendra Hans, welcome you to the seventh day of the FDP on Deep Learning, which is sponsored by E&ICT Academy, Ministry of Electronics and Information Technology. So, we welcome you to the session, sir. I hope your expertise will be very much helpful for the participants, as we already have seen some introduction about SNNs. So hopefully this session will be very much fruitful to all the participants. So hope you will enjoy the session, and definitely you will take the concepts and apply in your research domains. So thank you, sir. Thank you for joining the session. And now over to you, sir.
Thank you, sir. Thank you, Vikas, sir, for the nice introduction. So I feel privileged to be a part of this FDP. So here we are going to start with the spiking neural networks. So already there was a session on spiking neural networks. I was present there. So we have seen the introductory part. So here I'll go more with the mathematics and what are the main issues, challenges of spiking neural networks. So let's get started. So good evening all. So we're going to start with this session. So here in the spiking neural network. So am I audible? Am I audible?
Yes, yes, sir. Yes, sir.
Okay. Thank you. So introductory part of spiking neural networks we'll discuss. We'll discuss with the principles, applications, and future scope.
Sir,
So
are you
yes.
sharing any slides, sir? Slides?
Okay. So is it visible, sir?
Yes, yes, sir. Now it is visual.
Okay. So we'll start with this introductory part of spiking neural networks, principles, applications, and future scope. So let's get started. So these are the outlines uh, that we'll see one by one in this session. First of all, we will discuss about the introductory part. What is a spiking neural network? And then why we need it. I mean, what is the importance of spiking neural network in the uh, recent domain? And then applications in real world domain. Then we'll go to how spiking neural network works. I mean, what are the major steps we need to follow to work with spiking neural networks? We'll show one by one: neural coding, synapse model, neuron models, and then learning algorithms. And then we'll see some of the issues and challenges with spiking neural networks. And then how to simulate those spiking neural networks. So what are the tools and frameworks that we can use to work with spiking neural networks? And then future scope, and then some of the references. So first of all, what is a spiking neural network? So all of we know from the concept of uh, artificial neural network that artificial neural networks try to mimic human brain, right? So if we consider the earlier generations of neural networks, like the first generation, if we talk about perceptron, and then the second generation, the artificial neural networks, we can categorize spiking neural network as the third generation of neural networks. So it is considered to be the third generation of neural networks. So in mathematical term, if we define what is spiking neural networks here in this, okay, so before that, I'm going to inform you that in this session we are going to actually see the mathematical equations and what are the ways how we can use spiking neural networks rather than those biological backgrounds, because all those are already discussed in the earlier session. So SNN can be defined as a finite set of spiking neurons. These spiking neurons are the basic elements of spiking neural networks. Then a finite set of synapses. Synapses are those connections where the information exchange takes place. And then synaptic weights, we know from artificial neural networks that we have a connection strength between the neurons. So if we say that two neurons are connected, then how strong those connections are. So to represent that, we use synaptic weights. Uh, and then a response function. This response function here, we will see in detail in the upcoming slides. This response function is nothing but a neuron model. So there are various neuron models of spiking neural networks. So we'll see one by one. And one new thing that is not there in the ANN, I mean, second generation artificial neural network, that is firing threshold, theta. So we'll see why it is there. So spiking neurons use precise timing of spikes for information processing, akin to biological neurons. As we know from the neuroscience research that our brain processes information in the form of time, right? So spiking neurons also, because here our intention, one of the major intention is to mimic the biological brain to some extent. We know our biological brain is a very complex thing, so we cannot claim that okay, we are going to mimic 100% of the brain, but to a great extent we want to mimic it so that the complex task we can solve. Okay, so the spikes are discrete events. These spikes are discrete events that takes place at any point of time rather than continuous values. So this is about the information processing behavior of spiking neurons. Now, why? Why we are interested in one line? If we say here, we'll discuss in detail in the upcoming slides that SN is computationally powerful. Now, why it is computationally powerful? To understand it, we need to go through the various points that we'll do in the upcoming slides. And it is biologically plausible. The meaning of biologically plausible is what? It is going to mimic the biological brain to a great extent. And then energy efficient. Why it is energy efficient? Here in one point, if I say that due to the discrete spiking events, and the temporal information, it is energy efficient. And due to this property, energy efficiency, these are the four neuromorphic chips that I listed here. First one is from IBM True North. So this is a neuromorphic chip where spiking neural networks are implemented. And then the second one, this is from Intel, that is Intel Loihi. So this is also a neuromorphic chip. Third one, it is a DARPA quadcopter, and the fourth one is TNG chip. So all these are neuromorphic hardwares, means SNNs, spiking neural networks, are implemented in this. And due to the energy efficiency and biological plausibility, the research is going on in this field. So now, why spiking neural network? What is special about it? Spiking neural network. Okay. After that, we'll see that okay, when we talk about spiking neural networks, we talk about energy efficiency, biological plausibility, computationally powerful. But why it is not that much popular as artificial neural networks? That also we'll see gradually. So why spiking neural network? The first thing is that it is computationally powerful. The meaning is it smoothly works on nonlinear data without any hidden layer or hidden neurons. Now, here to understand this point, we need to discuss this point briefly. The thing is, we all know that in case of nonlinear data, if we want to deal with nonlinear data, let's say for a classification problem, we are dealing with nonlinear data. And we are using artificial neural networks. Now, if you do not use any hidden layer or hidden neurons, your separation will not be a well separation. We all know that. That's why we add more and more hidden layers. But what is the problem with hidden layer? The first thing is that it will increase the complexity, computational cost. The second thing is that actually we do not know how many hidden layers should be there. So when we do not know how many hidden layers will be there, so it is a trial and error thing. So if we do not know how many hidden layers will be there, we don't know how many hidden neurons will be there. So if we have a neuron model that is very powerful, then actually we don't need hidden layers or hidden neurons when we work on simple non-linear data. If the data is very highly nonlinear, then in that case we can think about hidden layers, but not as much as hidden layer as we have seen in artificial neural networks. So in this point, I would like to say that we also worked on this area and we removed hidden layer. Still, it was able to classify nonlinear data in a very successful manner. So second point is that biologically plausible. As I said earlier, we try to mimic uh, biological brain. Why? The reason is the biological brain is so powerful. It is massive complex. It is a massive parallel. So it has the ability to solve complex tasks. So if we can somehow mimic our brain to some extent, that will be a great help. So it closely mimics the human brain and then that of ANN models. Now we'll discuss these points in a detailed way. So therefore, the ability of solving complex tasks is much higher. So, and the next is energy efficiency. As we said, that if the information process that is, if it is temporal information, I mean the time information or the discrete events, then storing those things in a hardware, it will take less energy. So it consumes less energy and operate on ultra low power neuromorphic hardware. The neuromorphic hardware that we have seen earlier, Intel Loihi and IBM TrueNorth. So where it is suitable, I mean, what we'll do with the energy efficiency? So it is suitable for edge computing and IoT devices where battery life is crucial. We can think about making the devices for health monitoring. So, and the next is development of neuroprosthetic system. You see, when we talk about neuroprosthetic system, so if we have a model that is that mimics human brain to a great extent, right? Then we can think about developing those neuroprosthetic systems to help people. Now, why biological plausibility matters? Now, when I say that biologically plausible, why it matters? Why does it matter? Because it helps neuroscientists test hypotheses about brain function and disorders. You see, our brain operates with extremely low power, about 20 watts. Still, it performs complex cognitive tasks. So that's why biological plausible matters. Plausibility means biologically more realistic. So if we have a model of that kind, it will be a help for us. Now we'll see some of the applications in real world domain. So we can use SNNs, spiking neural networks, in classification problems, clustering problems, extraction of principal component analysis, time series analysis. I have given the references where you can find those papers where they worked on those things using spiking neural networks. And then robot control, trajectory making of a mobile robot or phototaxis. So this is what robot moves in the direction of light source, so we can manage that thing using spiking neural networks. And then the most important here is the brain inspired computing. It is opening a door towards brain inspired computing. So nowadays, so we are talking about quantum computation. So quantum computing and this neuromorphic computing, this two can be side by side. We can compare these two things. So biological neural structures, to understand these things, visual cortex or models of memories, these things, to understand these things, we can think about spiking neural networks, because we are trying to mimic our human brain. So if we can simulate in some neuromorphic hardware, we can understand it properly. Now the basic working principle. Now we talked about spiking neural networks, introductory part, and then we talked about its application, the motivation, why we need it. Now we'll see a little bit about how it works. And then we'll go to issues and challenges, why it is not so popular as NN, and what was the problem. So the basic working principle here, the core idea is what? A spiking neuron does not transmit information at each propagation cycle, meaning it transmits information only when its postsynaptic potential reaches a threshold. Now, we will understand with these two diagrams. In the left hand side, if you see the biological neuron, so here we know that this is the cell, right? So here the receivers are what? The receivers are the dendrites. Dendrites receives information, and after receiving information, something happens here, right? And that something is the mechanism that we'll see here. So this is called presynaptic cell. So here membrane potential raises. So when membrane potential, after rising the membrane potential, if it crosses a threshold, certain threshold, I mean, if I remember, it is about minus 50 millivolt for brain. So it may differ. So if it crosses that thing, then it will spike. Means it will send a signal through that action, and then it will be received by another neuron. I mean the dendrites of another neuron. So the information exchange takes place in this synaptic terminal. This we generally say synapses. For simplicity, we call this we only mimic these synapses. So now how information is taking place through neurotransmitter release and all this thing, biological detail, I'm not going into that thing. I'll just show you how to model a simpler mathematical way, how to think mathematically we can, so that we can mimic some part of this biological working. Now it is categorized that okay, the sender neurons are called presynaptic neurons. This will send this will send information, and the receiver neurons are called postsynaptic neurons. Now the sender neurons or the presynaptic neurons, these neurons will send information. Now when it is sending information, this information is in the form of spike. These are temporal information. So these spikes are being sent, and it is exchanged through synapses. After receiving these spikes through synapse model, now how to model this? There is another thing called synapse model that we'll see. So we can have several synapse models here. So after going through the synapse models, so it will go into this postsynaptic neuron, right? So we have several neuron models like LIF, Hodgkin Huxley, so the SRM. So these are the neuron models we'll see. So those neuron models have dynamics of its own, right? So after receiving the information, so using, we can represent this using differential equation that we'll see. The postsynaptic potential, this is called postsynaptic potential. So here for the potential of this postsynaptic neuron, so when it reaches a threshold, then there will be a spike sent by this postsynaptic neuron. Now this thing is depicted here. So here you see this side when time goes on this way. So PSP, postsynaptic potential. So it will rise postsynaptic potential, and so like that it will go. So when it reaches a threshold, let's say this is the threshold, defined threshold. So when it will cross this threshold, there will be a spike, and after spiking, it will directly come down, and it will not directly go to the resting potential. It will go to the reset potential. So it will pass this thing, and after that it will go to reset potential. And after that, if we want multiple spiking, then again it will go, and if it crosses the threshold, then there will be a spike. Now why we want to record this spike? So the time when there is a spike, that time we will record, right? So that time is very important, and the first spike is always very important. There is a concept called first spike. So that is being implemented in various neuron models. So we'll see that thing. So this is the mathematical equivalent of how we can think about the information exchange of this temporal information in case of spiking neural network. Now, here, if you closely observe, here 4 things we need to work with spiking neural network. The first of all, the question is, if we want at the input layers, if we want the temporal information, from where we'll get the temporal information at first? Well, let's say we have data, we have extracted the features. Okay, so after extracting the features, those are the continuous real value. So means we need to do something there in the continuous, real valued feature. We need to do something to make it spikes or to convert those into spikes. So that is called neural coding. So we have several neural coding techniques like population coding and rate coding, temporal coding, latency coding, various codings are there. So using those codes, we will transform real valued features into spike trains, and those will fed into the input layer. So that is the first step. Second, what we need when we send information through synapses, we need to model this synapse using some models like uh, we can use kernels like alpha kernel or double decaying kernel. These are there. So with the help of kernels, we will again transform these discrete spikes into continuous. Otherwise, we will not get this kind of shapes. So how to model those synapses? For that, there will be a synapse model, right? And after selecting synapse model, and one more thing, and there will be connection strengths in the synapses. I mean, those are the synaptic weights we call, right? So whether the synapse will be excitatory or inhibitory based on the weight, it will do that. Like whether the weights are negative numbers or positive numbers. So based on that, we will decide whether the synapse will be excitatory or inhibitory. Okay, whatever. So after that second step, after deciding the synapse model, how we'll implement the synapse model, and then we'll go to a neuron model. Okay, so we'll select a neuron model. So LIF is there, SRM is there. There are various neuron models. Okay, so those out of those neuron models, we'll select a neuron model there, and then according to the dynamics of that neuron model, will work. Now after that, what we'll do? Let's say, for example, here we wanted a spike at, let's say, for example, 10 millisecond, but the spike that we got, that was at maybe 5 millisecond, maybe 15 millisecond. If it is not 10 millisecond that we wanted, so there is error. I mean, it could not classify completely. If I talk about classification problem, means we need to do something to optimize it. That is called training, we know. So is there any training algorithm like backpropagation, as backpropagation is there for ANN, artificial neural network? For spiking neural network, the major problem is with the training. The training part is the major problem. We'll see why. Okay, so again, if I just magnify it in a way to understand more about the spiking, because that is the main concept of spiking neural network. So after firing a spiking neuron does not fire another spike immediately. That is called refractory period. At that period, it will not spike more. So rather than spiking, its PSP decreases and goes beyond the value of resting potential to the reset potential. Here you see, so from here, if I see, it is going up, and then it overshoots here, okay, and again repolarization. So here it should stop here, resting potential. No, it will not stop here. It will go beyond that refractory period. So here it is called, this area is called hyperpolarization. So during this time, it will not spike. So this is called a refractory period. So after that, maybe if any kind of excitatory kind of input is coming, then again the PSP will rise, and then again it will cross the threshold, we'll get another spike. That is a different story. But this is how it works. The membrane potentials, the relation between membrane potential and the spiking behavior. This is also called action potential, right? So now, okay, we want to compare between ANN and SNN. ANN, I refer to the second generation neural networks. Those you can think about multi-layer perceptrons or any equivalent model, like where we use sigmoid transfer function or activation function, ReLU, softmax, this kind of thing. So that is considered to be the second generation. So if we compare, you see the signal type in ANN is continuous, in SNN it is discrete. Now if you think here at this point, you have a very powerful algorithm to train ANNs, that is backpropagation, where delta rule is used, using finding derivatives to show the error direction and all. Why it is applicable there? Why you can do that? Because the signal type is continuous. If the signal type is not continuous, can you think about calculus there? No, we cannot do calculus there, right? So that is the problem with SNN. We cannot do backpropagation there. So, and there is no single algorithm that claims to be like, the replacement of backpropagation. Nowadays, there are algorithms like surrogate backpropagation and all. So we'll talk about other learning algorithms. So time representation is poor because here in SNN we know that the information is exchanged in the form of time. Energy efficiency. Are ANNs energy efficient? No, because we have a real values to work with, so we need to care about the precision when we want to store that thing. But in spiking neural network is high because these are the discrete events, right? Biological possibility of a spiking neural network is very high compared to ANN. ANNs are very small, simple mimicking of a human brain. And the real-time performance, if I talk about, it is moderate, and SNN is excellent. Why real-time performance is excellent? Because gradually the PSP will rise, so it will evolve over time. So it is dynamic system. Learning paradigm, the major learning paradigm that for which ANN is so popular, and now people are working in deep learning and all. So that is nothing but neural network. By adding more and more hidden layers, making the network deep. SNN, one learning algorithm that is based on Hebbian learning, as our brain learns based on the plasticity concept, that is synaptic time dependent plasticity, that we'll see here. Okay, so to work with SNN, the four things that we need already we have seen. The first thing is neural coding. This will do what? How the real valued inputs will convert into spike train. And then Synapse model, through which the information will pass to the neuron, spiking neuron. And the third one is the neuron model. There are various neuron models. And then fourth one is the learning algorithm. Now, one by one we'll discuss. Now, neural coding. So what is neural coding? How real valued continuous inputs are mapped into spike times. That is the meaning of neural coding. So there are various neural coding techniques, or you can say encoding techniques. So one is population encoding, and temporal coding, rate coding, and latency coding. Now, so out of all these, population coding is very popular. So I also worked on population coding, so I'll discuss population coding here. So other coding techniques you can also study. So in population coding, what happens is that information is represented by collective, a group of neurons. So here we'll use Gaussian functions. In population encoding scheme, each continuous real valued feature is mapped into a number of encoding neurons. Means you need to decide how many encoding neurons will be there. So those many Gaussian functions will be there, right? So that's why it is population. I mean, one feature you are going to map into different number of encoding neurons. So how it is done, we'll see the mathematics and the one example that I'll show you here. So using population encoding strategy, if let's say for example eta number of encoding neurons are there, then the real valued feature, let's say xf is a real valued feature, a value. Let's say from the feature matrix, a value is there, right? So f belongs to 1 to f is the total number of real valued features. So that will turn into a set of presynaptic spike timings. So here, for example, in the diagram, if you see here, you see n1 to ni. Let's say, for example, for the simplicity, let's say there are three neurons, and we want to do population coding. Okay, so for each neuron, if I say that okay, number of encoding neurons will be 4. So for each neuron is 4. So there are how many in input neurons? 3. So for 3, it will be 3 into 4, 12. So 12 number of encoding neurons will be there in that case. So that is what is mentioned here. So thus a single value will be transformed into spike trains. And now what will be the range of those spike timings? Like it will be from 0 to p reference. You need to choose a reference there, simulating time, that is called, right? So that simulate within 0 to that simulating time, your spike will lie. Okay, so that is the maximum encoding time. Okay, now let's say for example input data xf. So each receptive field neuron, let's say q belongs to one to encoding neuron. Eta was the number of encoding neurons. Okay, so this is in a closed interval, so including these values. So here the firing strength, let's say g, okay, of q means what for this particular neuron, and f is what that feature value for which we are doing it. Okay, so it will be the response values will be calculated using this equation. That is equation number 1. Now this is what exponential e to the power xf minus mu q. This mu is what the mean of, since we mentioned Gaussian function, so there will be mean and standard deviation. So mean is mu q and the standard deviation is sigma of that Gaussian curve. So these are defined using this equation number 2 and 3. So mu is calculated using this equation, and then sigma, that is standard deviation, so that is calculated using this equation, right? So and now here if you see uh, that there is a term called beta. What is beta? Beta is the adjustment factor that governs Gaussian curve overlapping. Means how much overlapping should be there between two or more Gaussian curves. So that will be decided by this adjustment factor. Now, based on the experimental analysis, we have seen in various experimental analysis, um, people have taken the value of beta to be 1.5. I mean, that works best for overlapping. So if somebody tries with other values, they can experiment it with the other values. So now here, practically, if we talk about encoding, like how the real valued features will be converted into spike train. So that is the first step, right? So these things we need to fed into the input layers of that model, spiking neuron model, a neural network. So you see, finally using that equation number 3, we'll get this response values, right? From we'll put this thing into the response values derived from equation number 1. Then xf is transformed to a set of pre-synaptic spike times using equation number 4. Now here what is T reference? That is the maximum time for the simulation we have seen. Okay, and 1 minus those responsible. Now understand this using this diagram. Now let's say for example these values I have taken from let's say a data set. I forgot, maybe it is ID's data set or something like that. So there were 4 features. Now you see these are the real valued features. Let's say you have a data set where 4 features are there. This is one feature, x1, x2, x3, x4. Let's say these are the 4 features. So for a single I mean for this sample, for a sample there are 4 features. Now let's say for example this red colored value, this is the real valued feature we are calling. Okay, so 0.641026. For this, if we do encoding using population coding, so what are the values that we'll get? Those values will be the spikes for this particular value. Now you see, if we draw it in the x-axis real valued feature, you see you can here see that 0.641026. So here it is 0.641026. Now 0.435897. So somewhere here, right? 0.1 something. So here it is, right? And then 0.01 sorry, so here it is. So then 0.0128205. So here's so somewhere it is here. Okay, so when I put this thing in the x-axis, the real valued features here, now I will choose how many encoding neurons will be there. Now let's say for example 4 encoding neurons I have just taken 4 encoding neurons. Means 4 Gaussian curves will be there. Now you can see here curve number 1, 2, 3, 4. These 4 Gaussian curves are there overlapping by a factor beta 1.5 I have taken there. Let's say. Now you see how I'll record the response functions. So 0.641026. So now if you come to this point 0.641026, if you see this vertical line here, you will record the points where it intersects with the Gaussian curves. So in the first curve, so it intersects at this. I mean, if you just take it, uh, what will be the value? 0.00016. So this is the value. I mean, actually, this value is this value I got from here in the y-axis, right? So and then in the second curve, it intersects at this point. That is also something 0.028. This is the value. Okay, exactly, it is not visible here, but you can understand. Okay, and then curve number 3, so it intersects here, somewhere here, right? So somewhere here means what, 0.5 something. Okay, so here, and then the curve number 4, so here it intersects 0.9 something. Okay, so these are the response values. Okay, so where it intersects. So after finding the response values, so we'll do what now? We'll find the spikes. How? T reference we have taken 10. So 10 into 1 minus that response value. So first response value is what? 0.000. We can consider it as 0. So 1 minus 0, that is 1. 1 into 10, that is 10. Right? So similarly, means we are rounding it to the nearest value. Okay? And then also T reference is 10. We have taken 10 millisecond. You can take different values. So I'm just showing that to understand the encoding process. And then like that, it is also 1 minus 0.02 something. So if you multiply with 10, so it will give approximately 10, then 5, then 1. Now you see, these are what? These are the spikes. Now these 4 spikes are for this single real valued feature 0.641026. For this thing, we have 4 spikes: 10, 10, 5, 1. Okay, so like that, we'll get the spikes for other things, and then we'll replace all the real valued features with spikes. So if we want to show the raster plot, we can show this plot, neurons versus spike time. So this is the encoding process. Now these kind of spike trains will supply to the neuron model, right? Now through synapse model, we'll pass those things. So let us understand synapse model first. So it is what a mechanism to exchange information between pre and post synaptic neurons. So synapse models can be implemented using different kernel functions like alpha kernel, double decaying kernel, hybrid kernel. We made a hybrid kernel also, so that one of my publications was there. We made the kernel hybrid also. So using alpha kernel, double decaying kernel, or to handle noises, we used Gaussian kernel there also. So we can use different kernel functions there. Okay. The synapses are present in the connection between two neurons. So these are specialized junctions where the exchange of information takes place between two neurons, right? So now there can be two types of synapses. One is excitatory, one is inhibitory. So this term can be interchangeably, I mean, it can be different, but generally we say excitatory and inhibitory. Now, if you see this two diagram in the figure number A, if you see, so here you see I and J, these are the two neurons. Let's say this I is the input presynaptic neuron, and J is what? Postsynaptic neuron. And this connection is what? This is the synapse, let's say. Now, just for the understanding purpose, okay, so there is no specific meaning of these symbols, but these diagrams there, okay, to just to understand it. Let's say this is a spike, okay, this is a spike T I, okay, the spikes we got from the input encoding. So now this spike will be transformed through synapse model. So there are various kernels. I said, let's say we're using alpha kernel. So when I pass that spike through that alpha kernel function, so it will give me this kind of output, right? Again, it is going to convert into the continuous thing. So this is called input stimuli or input stimuli. Okay, so then it will be multiplied with the weight. That is what we call synaptic weights. These are random, right? Random synaptic weights. Due to the randomness in the synaptic weights, we need to train. Otherwise, we would know beforehand that what are the optimal values of the synaptic weights. Then we did not to train. Okay, so those random with those random synaptic weights, it will be multiplied. So after, if now if let's say this weight is a positive value, so if we multiply the positive one, then we'll call excitatory postsynaptic potential, EPSP. then I have shown it here like that. I mean, it will be, it is responsible to raise the PSP if it is positive, because we need to go towards the threshold as we have seen in the earlier diagram. If we want to go towards the threshold, means we need to increase PSP gradually. If PSP decreases, then it's a problem. It will take time to go to that threshold. Now, so here it is in the case of positive weight. Now let's say your weight is negative, because you don't have control over that thing, right? So if you generate that thing within a range, there can be positive, negative values. Let's say -1 to +1. We don't know how the distribution will be there, right? So how many negatives and how many positives will be there? It's random. So negative numbers will be there, right? So if the weight is negative, then rather than increasing, it will decrease. It will decrease the PSP. I just showed this thing in the different direction at the below to identify. I mean, to demonstrate that it is decreasing the PSP. There is no specific symbolic meaning in that way. Okay, so it is called inhibitory postsynaptic potential. So in that case, we need to do more struggle to reach to the threshold. So we expect that our synapse becomes more and more excitatory. But if there is inhibitor, we need to handle somehow. That is also a challenge. We'll see this challenge also in the upcoming slide. That is also a challenge in spiking neural network. Means you need to ensure that okay, at least one spike will be there. Now how you can ensure it? If more and more negative weights are coming, then what? Okay. Next is the neuron model. Now we understand, up to this we understand how to encode and then synapse model, and then we'll come to the neuron model. Okay, so these are what this control the dynamics of spiking neuron, that changes the internal state of the neuron. If internal state is changing, means what, there is something happening. I mean, in the PSPs it may cross the threshold. So there are four uh, uh, neuron models I mentioned here. There may be more than that. The most popular is Leaky integrated fire, that I also used in my research, and it is Hodgkin-Huxley. Here you see Hodgkin-Huxley model. It is very complex, very complex. So this I guess these two people got the Nobel also for this work or some other work, I don't know, but this is the complex one, complex neuron model. Another model is spike response model and EGK based model, but most popularly people use Leaky integrate and fire neuron model for the simplicity, and the most of the research are done using Leaky integrate and fire model. It is also very powerful. Actually, it does what we implement this using RC circuit, a resistor capacitor circuit. So I'll not go into that thing in detail. Rather, I'll go with the differential equations and all these things needed for implementation or an understanding purpose. Now, this is the equation number 5. Using equation number 5, if you see here, there is a small change in the postsynaptic potential that is indicated by VM, membrane potential, over time, right? So when the time will go on, so in that way, so we will have a change in the PSP, postsynaptic potential. Using this equation, if we simplify, so this tau is what this is called the membrane time constant. This is nothing but Rm into Cm. The C is the capacitor and R is the resistor. So I have seen in here in this FDP. So earlier there was a session on spiking neural networks. So there these things are well discussed, very in-depth discussion was there regarding this, how we can think about biological things to implement here in the spiking neural model, and about resistors and capacitors also, how RC circuit is there, what are the responsibilities, and all these things are discussed. So I'll just discuss here the mathematical and the implementation purpose, right? So here it controls the shape of the PSP, this tau. So if you vary it, so the shape will change. Now here you see, if I from this equation number 5, so if I take this VM, I mean the small change, the D means what here is the small change, right? So small change in the uh, membrane potential, that is denoted by VM. Okay, so if I take it this way, so this thing divided by tau m. So now here is what dt is what the time step. So you need to choose the value of time step also wisely. So timestamp means if you choose that timestamp is 1 millisecond, after every 1 millisecond you will get that update, right? So at each value of dt, the value of VMT changes according to the equation number 7. So now equation number 7 is here. So you see, so if earlier the potential was this value, VMT minus 1, the earlier value, so we'll add the small change now we have, right? D VMT. So this will get from equation number 6. So after getting, we'll add that small change with the previous value here. Then we'll get the update at time t for the membrane potential. So now the value of membrane potential is what? VMT. So that is equal to the previous value plus the small change that had happened right now, right? Now for the nonlinear input stimuli, so IT here you can see this IT, we can represent this IT using different kernel functions like alpha kernel and double decaying kernel. I have not mentioned here, so you can use different kernel functions here. So that is called input stimuli there, right? So this equation is the main equation using which we'll get the updated value of the membrane, right? And now after getting that VM, now here you see at time t, if our membrane potential is VM, and let's say at time t hat, if that VM value crosses a threshold, this theta is what? The threshold, the defined threshold. If that value is greater than equal to the threshold, then LIF neuron fires a spike, which is recorded as spike time t hat. Means why? Because at that time, at t hat, the membrane potential crosses the threshold. So if at time t hat it crosses the threshold, means what? At that time there is a spike, right? So that spike will record. That is our information using which we'll find out the loss in the network, and then we'll train it, probably if required, then we'll optimize it. Okay. Then after firing a spike, as we have had a discussion earlier also with the help of a diagram, that after firing a spike, VM resets to a reset potential, right? So let's say now you want multiple spiking. So in case of multiple spiking, there is one absolute refractory period that we have shown in the earlier um, slides. So diagrammatically, so during that period there will not be any spike, right? So after that period is over, there will be again spiking activity. So to represent that mathematically, equation number 8 helps us to represent that thing mathematically. So if let's say you want multiple spiking, then you should add this refractory period with the equation number given to 5. So this is the equation number 5. You will add this refractory period if you want multiple spiking. If you want single spiking for simple tasks like classification and all, you can do that. But in case of multiple spiking, also the first spiking is very important. That is where is the proof of that thing? That is from the neuroscience domain. Okay, so here this is the Heaviside function. So t means but t r, what is t r? This is the time constant for refractoriness. At that refractory period, the time constant it is, and this is the Heaviside function. Ti are the spikes that will receive, right? And this is a Heaviside function. We know that this value is 1 if t greater than ti hat for a spike, let's say s. Otherwise, it is 0. So it is characterized by this equation. Now, for a postsynaptic neuron I, the spiking activity can be represented using equation number 10. Now, let's say here we have seen, here in this equation number 7, you see Vm over time it is changing, right? Now, if that value is greater than equal to a threshold theta, then there will be a spike at the time t hat, right? So if you want to represent it mathematically, we can say that thing. Okay, so t hat at I, so that spike will record if that thing is greater than equal to theta. This is what the membrane potential for a postsynaptic neuron I. That's why we have written I here, right? So this spike, this can be discrete events, right? 1, 2, 3 up to n. So the S is a set of issued spike times for a total number of n emitted spikes. So this is how our neuron model works. Now the dynamic of this neuron model, LF neuron model, this is so powerful that it can work on the simple classification task without even using any hidden layer. So because the dynamic is not so simple like ANN, like information is coming and then multiply with the weights and then pass through the activation function and get the output. No, it's not that simple. We need to take care in each and every part of the implementation. Now, after neural model, what? The most important part is what? The learning algorithms. Now, let's say you got a spike there, right? So at let's say 10 millisecond, you got the spike at output. Now, you wanted the spike at 10 millisecond, but you got it 5 millisecond or 6 or 7 like that, or maybe 11, 12, 13 millisecond. Means you need to optimize it. You need to bring close to 10 milliseconds. Otherwise, there will be error, right? There will be a difference. So for that thing, what you will do? So you will fine tune or optimize hyperparameters to reduce overall loss. There can be there are several loss functions using which you can represent that loss, and then you can optimize using learning algorithm. But there is a problem. The problem is, you see, as I told earlier, that SNN, maybe you heard about ANN most of the time. SNN also, maybe you heard about that thing, or maybe some of you are working on that thing, but it is not so popular as ANN. Why? The thing is, we do not have a back propagation kind of algorithm there in the SNN. It is still in infancy stage, we can say, the training algorithms of SNN. So SNN had remained unexplored due to the lack of efficient supervised learning. For unsupervised, we can blindly go with the STDP. But most of the classification tasks, for the most of the classification tasks, we need to have a supervised learning algorithm. So due to the lack of that thing, although it maintains a proper trade-off between computational cost and biological plausibility, it is unexplored in that way. So we have reviewed several supervised learning algorithms here. We have given the references. You can see different learning algorithms there, and you can develop your own. So traditional back propagation algorithm cannot be applied. Now, one question is that, okay, so why can't we use that traditional back propagation algorithm in case of SNN? The reason is for discrete spiking. If the curve is not continuous, though, how can we use calculus there? We cannot have derivatives, right? So for that thing, we need to think about something else. So although there are algorithms like spike prop and all, but those are not as successful as back propagation. We have also tried using meta heuristics and developed two models, SpyFog and OLIF. These two are our models. So I've given the references. One got accepted in scientific reports, Nature, right? So, but there we used meta heuristics. We give it a try to explore in the meta heuristic way how we can find the training algorithm. Now here I'll not discuss those things. Those are there in the paper. So the unsupervised one, the learning algorithm, that is STDP, synaptic time dependence plasticity. So that a little bit I'll just give it a highlight there. So synaptic time dependent plasticity is a biologically plausible learning rule that adjusts synaptic weights based on the pre and post synaptic spike. It is very simple to understand here. But the thing is, it can work with the unsupervised learning very well. But for the supervised learning, you have to do some tweaks. Now, those are not also that much successful. That is the problem. So, is how it works. If the presynaptic neuron fires before postsynaptic neuron, means delta t greater than 0. What is delta t? The difference between pre and postsynaptic. T post minus T pre. Postsynaptic, presynaptic. If delta t greater than 0, we'll call it as long-term potentiation, LTP, long-term potentiation. Now, if the presynaptic neuron fires after postsynaptic neuron, then delta t is less than 0. Here you can see. So in that case, we will say that it is long-term depression, LTD. These two are the primary factors there. So if delta t is greater than 0, then LTP, delta t less than 0, LTD. So based on that, A plus and A minus, these are the learning rates. Again, here we need to choose the values of these learning rates, and there are no certain rule to choose those values. Rather, you need to go with the trial and error and find the optimal hyperparameter values, or the experimentation done by other people there in that domain. So tau plus tau minus is there. So how we can think about the change in the synaptic weight delta W using this equation, right? So when delta t less than 0, this thing will happen. Delta t greater than 0, this thing will happen. Based on that thing, we can expect a change in the synaptic weights. You see, the training means what? We are in search of the finding the optimal values of synaptic weights, right? So if you know the optimal values of synaptic weights beforehand, that means you need not to train, because already you will get the right output. Due to the randomness in the synaptic weights that you generate randomly, that's why there is a problem. We need to optimize it. When we train, let's say for example we trained 100%, right? Now in that case what happens is that the synaptic weights that you got, that is optimal, right? So here, so there, if the weight is somehow it is changing, means what? Maybe it is going towards the optimal, right? So if it is going towards the optimal, then okay, it's okay for us. Okay, so this, if we depict using a diagram, we can depict it: long-term potentiation and long-term depression. And now, okay, so now we have seen the 4 stages, how to work with spiking neural networks, especially in the classification domain. So we have seen in input encoding, and then we have seen synapse model, then neuron models, and then training, about training, something we have seen. Now issues and challenges. What are the issues and challenges in spiking neural networks? You see, the first thing is that there is no general purpose efficient information coding technique. So you can pick any one of those things and you can do research on those things to explore that area. So efficient information coding technique is not there. Efficient, what do I mean by that thing? You see, you have several things like population coding, temporal coding, and then rate coding and all those things. There can be other techniques also. But which one is efficient? Can we say that, can we say in a certain way that this is the best way to encode, you use this method? We need to compare it. We need to compare and then implement, compare, and that way, we need to do trial and error in that way. So, and also one thing, like the way we transform, are we very sure that okay, this way our continuous values will be transformed into spike? There is a problem. So second thing is the unified framework. We don't have to compare between different neural models due to the variability. And now the third is what? Ensuring at least one spike within that decent range of that simulation time is very challenging task, as we have seen earlier also. We need to be very sure that okay, at least one spike will be there. And the last thing, the challenging thing is what? The supervised learning algorithm. You have several supervised learning algorithms nowadays. Surrogate back propagation, that learning is there, so we can explore that thing. So these are the tools and frameworks. Now we talked about spiking neural networks a lot, applications, how it works, this and that. So how we can simulate those things? Is there any simulators like that? So there are various. So I have listed these five. These five are most popular, having different features, along with the resources. These are the uh, official their sites to learn about. First one, let's say Brian 2. So this is based on a Python language. So if you want to simulate your spiking neural network, you have made a model, let's say for example, based on the theoretical concepts, and you want to simulate it, you can go and read those documents. So one by one it is there. So synapse, neuron model, all these things are there. You read those things and you can simulate. Second is SNN Torch. This is a Python based thing. This, you can say, special the design package for spiking neural network and deep learning with spiking neural network. People are nowadays trying deep learning with the spiking neural networks also. So, and another is BindsNet. So all this, for all this thing documentation, I have given the link, so you can go to the link and read those things. Nest is also there based on Python. And Nengo, the last one is what? If you want to work in the hardware, neuromorphic hardware like Intel, Loihi, IBM, True North and all, so you can go with that thing. So you can simulate and you can see your experimentation there. So these are the tools and frameworks. So what are the future scopes? So we'll see the future scope. In healthcare monitoring, so you can think about two wearable devices. So using which that there will be a great help in the healthcare domain. So you can develop those things using spiking neural networks. So if you think about low power consumption devices, so you can use neuromorphic hardware for that thing. Security, for the security purpose, surveillance and smart cameras. I mean, in the case of object detection and activity recognition, I'm working in activity recognition nowadays. So you can use spiking neural networks. So speech and audio recognition also, there also you can use spiking neural networks. And obviously in robotics and prosthetics, spiking neural networks are I mean, these are very popular due to the reason of that neuromorphic hardware. So these are the things, some of the work done by us in the epileptic seizure detection and all I have mentioned. So these are the references I have used, various references. So any queries? Any queries if you have, please ask. Because sir.
Friends, if you have any queries, you can or if you have any queries, you can put in the box. If it is any query, please write at box.
If you have any queries, you can ask or you can write in the chat box. I'll try to answer those.
Hello, Dr. Hussain. I think, sir, there is no query from the participant side. So that we can take a break of 10 minutes. Then we will start the next session at 6:15. Is it okay, sir?
Okay, okay.
Thank
Okay.
you.
Okay, thank you.
Please